Now that we have discussed the use of potential energies in a number of different contexts, we're going to cover here two important aspects that apply generally to potential energies. First, you'll recall that we obtained expressions for potential energies associated with interactions by beginning with the interactions expressed as forces, computing the work done by the forces inside our multiparticle system, and relating that work to the change in potential energy. In general, it's also possible to go the other way. Namely, if we have a potential energy associated with an interaction, we can calculate the corresponding force. Let's illustrate finding the force from the corresponding potential energy with the example of the spring potential energy. Let's consider the case of a spring mass system that moves along the x-axis. We recall that if we choose the origin x equals 0 corresponding to the position of the mass when the spring is at its relaxed length L0, then we derived earlier that the spring potential energy U sub s is equal to 1/2 k x squared. And by now we know how to sketch this potential energy on a diagram of the potential energy plotted as a function of the spatial coordinate x. Now if we perform the following operation, take the derivative of the potential energy with respect to the spatial coordinate x, that is, compute the derivative du sub s dx, and multiply the result by the unit vector corresponding to that same spatial coordinate, here the unit vector I hat. Then we have performed a mathematical operation called a gradient. Notice that even though we started with a scalar function, the spring potential energy, this operation is a vector operation because it produces a vector. Now by taking the negative gradient of a potential energy, we can find the corresponding force. This works generally for all potential energies. Here in this specific case, we find that the negative gradient of U sub s gives us minus kx I hat, which is the correct expression for the vector spring force in this problem. For a situation with only one spatial dimension, like we have here, we can use the graph of the potential energy to visualize this result. If we sketch the tangent line to a given point on the potential energy curve, then the slope of the tangent line is equal to the gradient at that point. And moreover, the negative of the slope gives the force corresponding to that potential energy at that same point. As a check for the sketch of the spring mass system shown, we see that x is greater than 0, so the corresponding point on the potential energy diagram would be something like this. The tangent line at that point has positive slope, meaning the gradient points in the positive x direction. However, the force is the negative of this slope, which means the force is pointing in the negative x direction. That makes sense since the spring is stretched longer than its relaxed length and, at this point, is exerting a force that is in the minus I hat direction. The second general aspect we want to discuss is the idea of path independence. To illustrate this concept, let's consider the gravitational potential energy for two binary stars, which we show here in an initial state and a final state. Now one could imagine there are countless ways in which the stars could move from the initial to the final state. But notice something interesting. The change in potential energy, the final gravitational potential energy minus the initial, depends only on the initial and final states. The change does not depend on the path between these states. This illustrates path independence, which is a general feature of potential energies regardless of the nature of the interaction. Now a special case of this is the following, where the initial state is the same as the final state. Again, one can imagine an infinite number of ways this can happen. Here's a question for you. What is the change in potential energy here? The answer is 0. Formally, we can work this out and we see that the expression is 0. This has to be true for any path, so in general, we say that for any round-trip path, the change in potential energy is 0. One final note on all this. Any interaction that has these properties, namely the force corresponding to the interaction, can be derived as the negative gradient of some potential energy, which exhibits path independence. Then that interaction is said to be a conservative interaction. The force is said to be a conservative force, meaning it's a force such that any energy transfers from work done by that force are always available for macroscopic motion of the system. Now, not all forces are conservative. For some forces, the corresponding work leads to energy transfers that make energy unavailable for the kinetic energy of the macroscopic system. Examples of such forces like this that we've already encountered include friction and air resistance forces. We'll see how to handle such cases using the energy principle in lectures that are coming up soon.